Okay, let's look at the solutions to worksheet 4.6. In problem 1, we have two matrices given, the matrix A and the matrix B. And they are row equivalent, so there's a sequence of row operations that transform A into B. We're asked to find the rank of A, and the rank of A is the number of pivots. It's the number of pivot rows, the number of pivot columns. They're all the same. It's just the number of pivots. And it's also the same as the dimension of column A. How many pivots do we have? We look to the echelon form, and there's 3 pivots, so the rank is 3. The dimension of null of A, we can see that also because there's 5 columns. 3 of them are pivot columns, so that leaves 2 free variables, 2 non-pivot columns. Each one of them is going to give a vector in the span of null of A. We're also asked to find bases. Find a basis for column A, row A, and null A. Those 3 subspaces. So for column A, the basis is the pivot columns of A. And we have to go back to A to get these pivot columns. We don't take them from B. So we identify the pivot columns. Here they are. Column 1, column 3, and column 5. So I just grab those from A. And 9, negative 10, negative 3, 0. There's the spanning set for column A. A basis for row of A are the non-zero rows. We can see them in B. We can also go back to A once we've identified those non-zero rows, but I can just take them from the matrix B. So 1, negative 3, 0, 5, negative 7. We're looking at that as a row vector. And I've got that together with 0, 0, 2, negative 3, 8. These vectors form a basis for row of A. Okay, null of A, basis for null of A. Here's where we have to do some more work. The matrix B is not in reduced echelon form, so we have to do a few row operations for that. And you can go ahead and do them. And here's what you should end up with. I've got still 3 pivot columns, but now I have zeros above and below those pivots. Okay, so after the row operations, I end up with this. And I just write this in parametric vector form. I have x1 minus 3x2 plus 1/2 x4, and that's going to be equal to 0. I have x3 minus 3/2 x4, that's equal to 0, and I have x5 is equal to 0. So one vector, and that's 2 free variables, right? 2 free variables. I've got x2 and x4 are the free variables. So the part that depends on x2 is going to be 3. X3 does not depend on it. X4 and x5 don't depend on it. And the part that depends on x4 is going to be negative 1/2. X2 does not depend on it. 3/2 for x3. x4 itself, and x5 does not depend on it. So there's the 2 vectors, and they will span null of A. So null of A is equal to the span of these vectors. They're both in R5 because there's 5 columns. and they form a basis because they're linearly independent. All right, in problem 2, a 6 by 3 matrix A has rank 3. Find the dimension of null of A, find the dimension of row of A, and find the rank of A transpose. Now we're thinking about the columns of A, and how many columns does it have? It has 3. And the rank is saying it's got 3 pivots. That means all 3 of those columns must be pivot columns. So that leaves no free variables. The dimension of null of A is 0. Null of A only contains the 0 vector and nothing else, and we say the dimension is 0. Okay, how about the dimension of row of A? Again, the number of pivots is going to tell us how many non-zero rows we have in the echelon form. Any non-zero row starts with a non-zero entry, and that is by definition a pivot. And so there's 3 of them. So that means the dimension of row of A is 3. There should be 3 non-zero rows in the echelon form of A. If we look at the rows of A as vectors, those are exactly the same as the columns of A transpose. And since there are 3 non-zero rows, there's going to be 3 pivot columns in A transpose. So the rank of A transpose is 3. And again, it's because 3 pivots. 3 pivots in A. And that comes from the rank of 3. Okay, problem 3. If a 5 by 6 matrix A has 4 pivots, what is the dimension of null of A? 4 pivots, that means 4 pivot columns. A has 6 columns, so that leaves 2 non-pivot columns. So the dimension 2 non-pivot columns, and that means 2 free variables. The dimension of null of A is 2. The next question is column A equal to R4. Are the vectors in column A in R4? Never mind whether the whole subspace is equal to R4, but how many entries do the vectors in column A have? You can see that the matrix A has 5 rows. It's a subset of R5, so it can't possibly be equal to R4. But where did this question come from? Well, it comes from the fact that the dimension of column A, we've got 2 non-pivot columns, 4 pivot columns. The dimension of column A must be 4. But just because the dimension is 4 doesn't mean it's equal to R4. The vectors are not even in R4. The next question, what is the dimension of row of A? And the dimension of column A and the dimension of row of A are the same. And so the answer to that is 4, same as dimension of column A. If there's 4 pivots, that must mean that there's 4 non-zero rows in the reduced form of A. Each one of those goes into a basis for row of A. And the same question, what about row of A? Is row of A equal to R4? It's got dimension 4. So is it R4? Once again, we're thinking about the vectors. Row of A is a subset of what? What do those vectors look like? How many entries? The matrix A is 5 by 6. So each row has 6 entries. That means row of A is a subset of R6. And so, no, it can't possibly be equal to R4, just because the dimension happens to be 4. Okay, problem 4. We have a system of 7 linear equations, in 6 unknowns. So this is going back to the beginning of the course where we were thinking about systems of equations. And before I even ask the question, let's think about what is the augmented matrix going to look like. The augmented matrix is going to look like this. I'm going to have the coefficient part and then the constants. The coefficients, there's going to be 7 rows and 6 columns, 1 for each unknown. And then this is going to be some vector b sitting out there in the last column, right, to the right of the equal sign, those constants. And the question is, can there be a unique solution? Can there be a unique solution for some set of constants here, for some b, I'll just call it, that's a vector b, the constants on the end of the equations. So is it possible to have 6 pivots? Can there be, really what we're asking, can there be 6 pivots? Can there be 6 pivots on the left side of that matrix? And the answer is yes, there can be 6 pivots in there, because the number of pivots, remember, is limited by not only the number of rows, but the number of columns. And there's 7 rows, so we could have 6 pivots in there. So that's a yes in this matrix, which would give us a unique solution as long as that last row is all zeros in the reduced echelon form. Okay, the next question is it possible for the system to have a unique solution for all b, for all columns of constants b? The answer is no, because it's possible that I might get a row of zeros to the left of this bar in the reduced echelon form, and then a non-zero entry out here, because I'm asking about all possible sets of constants. So it's the same as asking, does the columns of this augmented matrix here, do these columns span all of our 7? And they don't. They don't span all of our 7. Not only that, they can't span all of R7, because R7 has a standard basis with 7 vectors in it. Any basis, any spanning set for R7 must contain 7 vectors. So the answer is no, there can't be a unique solution for all possible b, but it is possible for some sets of constants.